Hello guys, welcome to Self-Help Maths Academy. Today we're going to see some of the examples on the derivatives. And the first example is, say, show that the function f of x equal to x square minus 1 when x is greater than or equal to 1, and it is equal to 1 minus x when x is less than 1. Okay, has no derivative at x equal to 1. So we have to show that this function has no derivative at x equal to 1. To show that, let's see how we start with a solution. So here they are saying that it has no solution at x equal to 1. So let's try to understand what is the function at f at x equal to 1. Okay, so as they have given you the given function at x equal to 1, x is greater than or equal to 1, it takes the value x square minus 1. So f at the point of 1, f at the point of 1 will become 1 square minus 1. This is 1 minus 1, which is equal to 0. Okay, now let's find out the left hand derivative at that point. Left hand derivative at a point. So by the definition, at a point, it is nothing but limit of f of x minus f at the point of 1 I want. So f of 1 divided by x minus 1, and here it is x tends to 1 minus because it is left hand derivative. So this is equal to, so what is our f of x? F of x, because it is x is less than 1, right? See, 1 minus 1 is less than 1 means the function is 1 minus x. You can observe. It is left hand derivative I am taking 1 minus. So when it is less than 1, so the function is 1 minus x. So I will take here 1 minus x. And our f of 1 we have already written, that is 0. So let me take this as 0 divided by, this is x minus 1. This is nothing but what? Limit as x is tending to 1 minus. Okay. Now this is equal to. Now let us write this here. What we do? Here we have to put, because I have to change the limit. We have to put, you know that in the previous session we have seen wherever x is there, we used to put c minus h if it is left hand limit, and c plus h if it is right hand limit. C is the point. At what point we are defining the differentiation. So here our c is what? At x equal to 1 we are trying to understand. So therefore put x is equal to 1 minus h. Okay, where h is what? H is greater than 0. Alright, so this is what is a substitution. So here this is your c. This is your c. If you see, in place of c I have 1. Okay, because at 1 we want to understand what is the differentiation. That is the important note. So now let us replace that all thing. So 1 minus here, in place of x I am putting 1 minus h. I will use one more bracket here. This is 1 minus h. 1 minus h, and this 0 I think we can leave, no problem. So divided by, here x means 1 minus h again, 1 minus h minus 1. So since x is tending to 1, if you see x is tending to 1 minus, as x is tending to 1 means this, if I take here x is tending to 1, this will become what? 1 is equal to 1 minus h. This cancels. It is h equal to what? H equal to 0. H tends to 0, right? So therefore here I'll write here as h tends to 0. So now simplify this. This is equal to limit as h tends to 0. This minus 1 plus 1 cancels, and minus of minus, this will be h here, and minus 1 plus 1 cancels. This is negative h at the bottom. Okay, so this is equal to, now h also we can cancel as h tends to 0. So 1 divided by negative 1, which is negative 1. Okay, so now this is our left hand limit. This is our left hand limit. Similarly, let's find out the right hand limit. Right hand limit at that point. This is equal to, this is nothing but again by the definition of a derivable function at a point, we'll write this one, limit as x is tending to 1 plus. Okay, so this is equal to, as you know, as x is greater than 1, so this is our function x square minus 1. So let's write that this is your x square minus 1, and f at the point of 1 is 0 upon x minus 1. This is limit as x is tending to 1 plus. Okay, so as you know, now again put here we have to put in, because it is right hand limit, so we have to put x as 1 plus h, and your h is greater than 0, which is positive. Okay, so this will be giving you limit wherever x is there, you write 1 plus h square, add as it is, this one is 0, leave it, divided by again 1 plus h minus 1. So here, as again x is tending to 1, this is 1 is equal to 1 plus h, so this cancels. As x is tending to 1, your h tends to 0, h tends to 0. Okay, so since it is a right hand side limit, so this is now what we got, 1 plus h 1 plus, sorry, here it is say 1 plus h the whole square. This minus 1 I have left here, please write that 1 plus h square minus 1. So now this is like a plus b the whole square, we can write as a square plus b square plus 2ab, that is 2h, this one, a plus b the whole square, and negative 1 upon this negative 1, positive 1 cancels upon h. This is limit as h tends to 0 plus. So this negative 1, positive 1 cancels. So from here we can take h out. So this is limit as h is tending to 0 plus. If I take h out, this is h plus 2 here divided by h. So this cancels here. Now as you see, as h tends to 0, you will get here, this one is 0 plus 2, which is equal to 2. So here you got your right hand limit, right hand derivative as 2. So your left hand derivative is equal to negative 1 and right hand derivative is equal to 2. So therefore left hand derivative is not equal to right hand derivative. Okay. So therefore derivative at x equal to 1 does not exist. Okay, it is not exist. Therefore when it does not exist, we say that what, f of x is not derivable at x equal to 1. Okay, this is how we have to check that the given function is derivable or not derivable. Here you see that it is not derivable. Okay, so this is how we will be talking about the derivability. Now let's see, we will take another function, say another example, say prove that the function f of x equal to modulus of x minus 1 is continuous at x equal to 1 but not derivable at x equal to 1. I think it's about the same thing. We have seen the modulus function at x equal to 0. It was continuous, but it was not derivable at x equal to 0. Okay, let's see this one. So first we will see continuity at x equal to 1. We will check whether that is continuous or not. Continuity say at x equal to 1. Okay. So given function is what? Given function is f of x equal to modulus of x minus 1. Let us find out the left hand limit first. To find out the left hand limit, we know limit of f of x as x is tending to 1 minus, because at x equal to 1 we have to check. So this is equal to limit modulus of x minus 1 as x is tending to 1 minus. So here, as it is left hand limit, we have to put, and at x equal to 1, so put x equal to what? 1 minus h, and h is greater than 0. So this gives us limit, I'll write this as 1 minus h minus 1, and here as x is tending to 1, your h tends to 0. So h tends to 0. Okay. So this is negative 1, positive 1 cancels, and modulus of negative h is, since it is in a modulus quantity, so it is h only, as h tends to 0. As h tends to 0, this is what? 0. Okay. This is our left hand limit. Okay. Similarly, let's see the right hand limit. For the right hand limit, we will consider limit of f of x as x is tending to 1 plus. This is equal to limit of modulus of x minus 1 as x tends to 1 plus. So here what we have to put? We have to put x equal to, since it is right hand limit, 1 plus h, and your h is greater than 0. So let's see what we get. This is now limit as h tends to, it will be 0 plus as x tends to 1, your h tends to 0. So this will become 1 plus h minus 1. This will be minus 1 plus 1 cancels, as h tends to 0, it is again 0, right? So therefore, your LHL is equal to RHL, and also we have to check whether it is equal to our f of 0, I mean f of 1 or not. So let us find out what is f of 1. F of 1 will be, since our function is x modulus of x minus 1, so it will become 1 minus 1. This is equal to modulus of 0, which is 0. So therefore, limit of f of x as x is tending to 1, this is equal to, because left hand is RHL is equal to LHL, so therefore the limit of function exists at that point, and also this is equal to f of 1. So hence we say that the continuity definition follows. Therefore, f of x is continuous. F of x is continuous at x equal to 1. Now let us check whether the given function is derivable. Okay. The derivability at x equal to 1. Let us check this one now. So for that we have first let us consider f at the point of 1. What is the function? It is 1 minus 1, which is equal to 0, because it is x minus 1, right? So now the left hand derivative is equal to, we know that it is also denoted by f dash of 1 minus 0, or f dash of L dash of f of 0, anything you can denote it with. So this is nothing but, by the definition, limit f of x, f at the point of 1 divided by x minus 1 as x is tending to 1 minus 0. So this is equal to, f of x is modulus of x minus 1. So this is modulus of x minus 1, and f of 1 we already found, that is equal to 0 upon x minus 1. This is limit as x tends to 1 minus 0. Okay. Now here we have to put, because it's a left hand limit, so we have to put what? We have to put x is equal to 1 minus h, and our h is greater than 0. So let's see what we get. So if we put that, so this will be limit of, this is 1 minus h minus 1 upon 1 minus h minus 1. This is as x is tending to 1, this h tends to 0, right? So this will become 0. Okay. So now this will be equal to, this one cancels. This is, as this is the left hand limit, and we are saying that it is h is tending to your function limit as, say, this modulus of h, this will be equal to h here, divided by this one will be negative h here, and h is tending to 0. So this is, as h cancels, it is negative 1. Okay. This is LHD. Let us find out the right hand limit. So right hand limit for this, again by the definition, we can write this as f dash of 1 plus 0. This is limit. These are all the notations. Okay. This I have already given you, divided by x minus 1, and as x is tending to 1 plus 0. So this is equal to, let me write this as limit. What is our function? It is x minus 1, and this is 0 upon x minus 1 as x is tending to 1 plus 0. So here, since it is the right hand limit, we have to put our x is equal to 1 plus h, and here your h is positive, right? So here this will give you limit 1 plus h minus 1 upon This is 1 plus h minus 1 as h is tending to 0 plus, because as x is tending to 1, your h tends to 0. So this will be h upon h. Okay. So this is limit h upon h as h tends to 0 plus. So this is simply 1. So here you have got your left hand derivative is negative 1 and right hand derivative is positive 1, which are not equal. So therefore LHD is not equal to RHD. Okay. So therefore, what is the conclusion? F of x is not derivable. Not derivable at x equal to 1. Okay. So this is another way of explaining that the given function is not derivable. Okay. Now let us see another example where we will see whether it is derivable or not, and how do we say that the given function is derivable at a point and it's not differentiable at another point. So those things we will see. Whether they're derivable or they're continuous. Let us check one another example. Okay. Another example. So here, given that f of x is equal to 1 plus x if x is less than 2, and f of x is 5 minus x if x is greater than or equal to 2. Okay. And we have to check whether the given function is continuous or and derivable. Okay. Check the continuity and derivability and continuity at a point x equal to say 2. Okay, let's see this. The given function here, they have defined this as f of x is 1 plus x if x is less than 2. If x is less than 2, this is equal to 5 minus x if x is greater than or equal to 2. We have to check at x equal to 2 whether the given function is differentiable or it is continuous. Those things we have to check. So for this, let us start with the first the continuity, and we will see then the differentiability. For continuity, let us see the left hand limit. So that is nothing but limit of f of x as x is tending to, your x is at 2 we have to check, so it is 2 minus 0. Okay, from the left hand limit. So this is equal to limit, as you know, as x is tending to less than 2 we are talking about. When less than 2 means the given function is 1 plus x. This is our function 1 plus x as x is tending to 2 minus or 2 minus 0. That is fine. Okay. So now we have to put, since at x equal to 2 we have to check. So put x equal to 2 minus h. Okay. And h is greater than 0. So wherever x is there, I'm going to put this one. So this will be limit 1 plus 2 minus h. This is as h. As x is tending to 2, put x equal to 2, the h will be tending to what? 0. Okay. So this will be, what do you get? This as 3 minus h here. So this is limit as h tends to 0, 3 minus h. This is as h tends to 0, this will be 3 minus 0, which is equal to 3. Okay, this is your left hand limit. Similarly, let us find out the right hand limit. This is equal to limit of f of x as x tends to 2 plus 0. Okay, so this is equal to limit as x greater than 2, we have your function as 5 minus x. Okay, that is your function. So let us take that as 5 minus x as x tends to 2 plus 0. So here we have to put our put x as 2 plus h. Okay, so here this is equal to limit 5 minus 2 plus h. Here as x tends to 2, your h will be tends to 0. This is equal to 5 minus 2 is 3. This will be 3 minus h, limit as h tends to 0 plus. Okay, so as h tends to 0, this value is again what? 3 minus 0, which is equal to 3. So here clearly you have got your LHL is equal to RHL, and which is equal to 3. Left hand side limit which is equal to right hand side limit which is equal to 3. Now we have to find out the function at 3. So limit, the function at the x equal to 2. So what is f of x as x is tending to 2? This is your at x equal to 2. This is given by this one, this function at x equal to 2. The function is 5 minus x. So 5 minus x, limit as x tends to 2. So put wherever x is there 2. This is 5 minus 2 which is equal to 3. If you see, your LHL is equal to RHL. This is equal to f at the point of 2. So this is the definition of continuity. Hence the given function f of x is continuous. This is continuous at x equal to 2. Okay, so continuity is decided. Now again we have to check for the differentiability. Now again for the differentiability, let us take the left hand derivative. This is now by the definition we know limit of f of x minus f of 2, because at x equal to 2 we are discussing. This is as x tends to 2 minus 0. Okay, so this is equal to, so as x tends to as x is less than 2, our function is 1 plus x. So limit, this is 1 plus x. F at the point of 2, we have seen f at the point of 2 already we have calculated, that is equal to 3. Let me write this, divided by x minus 2, and this is x tending to 2 minus 0. Okay, so after simplification, this if you see this one, if you want to simplify you can simplify, else you can just directly put here, since it is a left hand derivative, the x will be equal to 2 minus h. Put x equal to 2 minus h. So this will be limit 1 plus 2 minus h minus 3. This is 2 minus h minus 2. Okay, and as x is tending to 2, this will be 0. H tends to 0. So this will be what? This will be here you can just do the simplification. 1 plus 2 is 3 minus 3 is 0. So it is here limit minus h divided by minus 2 plus 2 cancels. Here it is minus h as h tends to 0. This also cancels. It is simply 1. Okay, which is free from h. Similarly, let us find out the right hand derivative. Right hand derivative by the definition, limit of f of x minus f of 2 upon x minus 2 as x is tending to 2 plus 0. Okay, so this is equal to limit this since as x is tending to 2 plus means it is greater than 0. So greater than 0 means greater than 2. Greater than 2 means the function is 5 minus x. Okay, so we will write it as 5 minus x. So limit, this is 5 minus x minus f of 2 we calculated, that is 3 upon x minus 2 as x is tending to 2 plus 0. Okay, now here since it is the right hand limit, so therefore put x equal to 2 plus h. So this will be limit 5 minus 2 plus h, okay, minus 3 upon, this is 2 plus h minus 2, limit as h tends to 0 plus. So 5 minus 2 will be 3 and minus h. So 3 minus 3, here you will get 3 minus 3 is 0, but here it is negative h divided by positive h, limit as h tends to 0. Here I can cancel h, but I still have what? Negative 1. So therefore the right hand side limit is 1 and the left hand side limit is negative 1. So therefore what we concluded, LHT is not equal to your RHT, the right hand limit. Okay, so therefore f of x is not derivable at x equal to 2. Okay, hence what we concluded, hence the f of x is continuous. This is continuous but not derivable at x equal to 2. Okay, so similarly I think one I'll give you all, please just try and comment your answers in the box. If suppose, let me give you this example. Let if I have f of x equal to say 2 plus x, 2 plus x, if x is greater than or equal to 0, and f of x is say 2 minus x for x less than 0. Okay, then check at x equal to 0 whether the function is continuous, whether it is continuous or whether it is derivable. So just check whether it is continuous at x equal to 0 or derivable at x equal to 0, whether it obeys both or one it fails. So whatever it is, just comment your answers in the you can put your answers in the comments. Okay, and just try this this example in a similar fashion as we did it in the previous example. Okay, so and we will see the answers, whether you will get the differentiability or the continuity at a given respective points. Okay, so I think maybe I think in the next videos, because it will become big, so therefore what we'll do, we will try to do some more examples in the next video, where we will try to see the given function is continuous or differentiable in the given intervals or in the at a given point. So those discussions we will do in the next I think video probably. Okay, I think till then, you take care guys, see you all in the next video. Bye bye.